to do 3.4. 3.4 is the hyperbola, which is very similar to the ellipse, but it goes out instead of going in. An ellipse is kind of like a stretched circle. A hyperbola is going to start, come in, and then slowly go back out. So it's going to be like kind of two U's facing away from each other. They give the official definition of a hyperbola is the set of points in a plane such that the difference of the distances from each point of the set from two fixed points, which are the foci, in the plane is constant. That's extremely similar to your ellipse definition from 3.3. Again, it is the set of points in a plane such that the difference of the distances of each point of the set from two fixed points, which are your foci, in the plane is constant. The main difference between that definition and the ellipse is the sum of the differences. The hyperbola is the difference of the differences. So you can see there they go through the distance formula and showing it just like we did in 3.3. So I'm not going to repeat that again. Down at the bottom in the box, they give you the first formula. So our formula for a hyperbole, and this is where it's centered around the origin, so centered at 0, 0, is x squared over a squared minus y squared over b squared equals 1. Just like with your ellipses, you want it to be equal to 1 always. So here it's equal to 1. You have x squared over a squared minus y squared over b squared equals 1. Similar to the ellipses as well, A is your vertex, B is the ends on the minor axis. So, we also have a C for your focus. We mentioned foci in the definition. So C, just like in ellipses, is going to be your foci. Because a hyperbole should have two, one for each arm. Right? They give you a picture down below as well, just showing that if you take the distance from one minus the difference of the other, it should be the same as taking the distance from a different point minus the difference from the other foci. Okay. Next, on the next page, they give you figure 3.34, which are all your pieces to your ellipse. So you have a graph. And on each graph, you have your vertex, which is at a comma 0. And you have a vertex on the other side, which is at negative a comma 0. All right, again, we're centering things around the origin for right now. All right, you also have your minor axis, which is going to be at b. So that's 0 comma b. And at 0 comma negative b. Okay. Next, we have our focus. We've done A, we've done B, so next is our focus. Our focus is going to be out past the vertex on the outside. The curve always opens up towards the focus. So on an ellipse, the curve opened up towards itself, so the focuses were inside. Now the curves are opening up away from each other, so the focuses are going to be on the outside. So your focus is at C comma 0 and at negative C comma 0. Again, just like ellipses, a ton of symmetry. All over the place is going to be your symmetry. What we're going to do next is we're going to work out the lattice rectum. So similar to ellipses, we had our lattice rectum. The length of the lattice rectum was 2b squared over a. Same thing in hyperboles. It is 2b squared over a. You'll figure that out. You'll get the length of the lattice rectum going up and going down on both sides. Length of the lattice rectum going up and the length goes down. The last piece that we have are going to be our asymptotes. So we know our parabola is going to go through the vertex and it's going to go through the ends of the lattice rectums, just like in ellipses. But we have asymptotes in hyperbolas. What keeps them from just going straight up? Getting through that one point and getting wider and wider and wider. So they each have two asymptotes that kind of control where the hyperbole goes. To figure out your asymptotes, you're going to create a rectangle between the vertexes and the B's, between A and B. inside that rectangle, you're going to draw two diagonals. Use a ruler. So make sure, and this of course is not to scale. My ends of my lattice rectum would be around here. That is the points, the dotted lines are where the graph is not allowed to touch at all, period. So you're going to start at your vertex, and you're going to go and you've got to go through the ends of the lattice rectum and just kind of follow those asymptotes on both sides, starting with the vertex, going through the lattice rectum, and following the asymptotes. It does not go through the focus, same with ellipses. So that's all your different pieces for a hyperbole. Another difference between a hyperbole and an ellipse. Since an ellipse is the sum of the differences, and a hyperbole is the difference of the distances. Ellipse is the sum of the distances, a hyperbole is the difference of the distances. Your formula for C has changed. So the way to get C is different for an ellipse as it is for a hyperbole. So you need to have both memorized and know which one goes to what. It tells you starting at the very bottom of 132, the last three words. For an ellipse, A is greater than C, C equals A squared minus B squared, and A is greater than B. Then it tells you that for a hyperbole, C is greater than A, and C squared equals A squared plus B squared. That is how the book tells you to tell the difference between an ellipse and a hyperbole. When A is greater than C and greater than B, it's an ellipse. When C is greater than A, it's a hyperbole. An easier way to remember that is on your sign. If it's a plus sign, it's an ellipse. If it's a minus sign, it's a hyperbole. So your sign's gonna be the easier way. The most important thing in that paragraph is the C squared equals A squared plus B squared. You need to know that. C squared equals A squared plus B squared. Remember in the last section, it was C squared equaled A minus B. So here it's a plus. If you want to go ahead and solve for C so we can easily find that, you have C equals the square root of A squared plus B squared. Once you take that root, you will have a plus and a minus, so keep that in mind as well. The next thing they mention is another formula that looks very similar to that, except for the x's and y's are in different spots. So the second formula they give us is y squared over a squared minus x squared over b squared equals 1. Now in ellipses, they gave us two separate formulas just like this. One where the x-axis is the major axis, and one where the y-axis is the major axis, just like what we have here. The difference is in ellipses, since it was a plus sign, we could use our commutative property of addition and things could get switched around real easily. So I told you then, don't worry about which one's first. Look at the larger denominator. Again, that is for ellipses. The larger denominator was the major axis. Hyperboles is different. Hyperboles is always whichever one comes first. Which variable came first? That's the major axis. With a minus sign, you can't really switch them around. It's always the positive variable. The positive fraction is that variable is the major axis. So it's a whole lot easier to tell which one's major, which one's minor. Okay? The next thing they're talking about is if the center is not at the origin. So far, everything we've done hyperboles, the center is at the origin. Just like circles, that's how we started off there. We started parabolas off, centers at the origin. Ellipses, centers at the origin, and then later we'd move it around to different places. So here we're going to move it and show you the equation to move it before we actually get into working with these. So the equation for moving an ellipse, or a hyperbole, sorry, if we take the x as the major axis, that's going to give you x minus h squared over a squared minus, because it's an ellipse, y minus k squared over b squared equals 1. So just like with parabolas, just like with ellipses, just like with circles, everything stays exactly the same, but wherever your x and your y is, you add minus h minus k. Make sure the h is always with the x and the k is always with the y. So when the y is your major axis, your y still has to come first, but k is always with y. So y minus k squared over a squared minus x minus h squared over b squared equals 1. Make sure whatever's first is your major axis. Your center is your hk. They're always opposite of whatever sign is in the equation. And it should always be equal to 1. Next thing we're going to do is the asymptotes of a hyperbola. We talked about them for a little bit when I was drawing the first graph. So your asymptotes of your hyperbole. You're given 4 equations. Well, you're given 2 at the very top of 134. Those 2 equations are the equations of the diagonals, which are your asymptotes. We want to find the equations of the asymptotes. You make a rectangle with the vertex and the b's. Then you do your diagonals. Those are your asymptotes. So they refer to them as the equations of the diagonals or the equations of the asymptotes, depending on who's formatting the questions. The first equations they give you is the equation of a diagonal, but only in the first quadrant. Doesn't really help us much. We need 2 different equations, and one of them never hits the first quadrant. So if you go about 2/3 down on page 134, it gives you 2 separate formulas. And each one depends on what your major axis is. So down towards the bottom of that page, you have y equals b over ax, and y equals negative b over ax. Then, a little bit further down, we have y equals a over bx, and y equals negative a over bx. They're 2 different formulas. They're going to depend on which axis is your major axis. So depending on if it's a y problem coming first or an x coming first, will depend on which set of these you use. The top ones, where it's y equals b over ax and y equals negative b over ax, is when your major axis is the x-axis. Meaning, when the graph is going away from the y-axis on the x-axis. The second one's the y equals a over bx and y equals negative a over bx, is when your major axis is the y-axis, meaning the graph is going up and it's going down. It's spread across the y-axis. Okay. Example 1, sketch the curve 36x squared minus 64y squared equals 2304. So we'll do that one first. So the first thing you have to do is get it into standard form. Sometimes that involves completing the square, sometimes it only involves making it equal to 1. Since we already have our x squared, y squared, we don't have a bunch of x terms, y terms, and a super long problem, all we have to do is make it equal to 1. You'll see the next example, we'll have to complete the square. So we need to make it equal to 1, you divide by the number by itself. This leaves us with x squared over 64 minus y squared over 36 equals 1. So from that, we can easily tell what A is. A squared is 64. A equals plus or minus 8. B squared is 36. B equals plus or minus 6. Your major axis is your x-axis because that's what comes first. It's the x. Okay. So we still need C. We still need the length of the lattice rectum. And then we'll have to find the equations of the diagonals. Actually, here all we have to do is sketch, so we don't actually need the equations of the diagonals. So C equals the square root of A squared plus B squared. That's our formula that we were given for hyperboles. Remember, it is different than the one for ellipses. So make sure you have both of them memorized. Make sure your formulas are memorized. And this is your ellipse one. So C equals the square root, A squared is 64, plus B squared is 36. That gives you the square root of 100. So C equals plus or minus 10. So here the center is at the origin. So that's going to be where we get to start. All we have left to do is to find the length of the lattice rectum before we just put it all onto a graph. So for your lattice rectum, our length is equal to 2b squared over a. Remember, that's the entire length, so we're only going to use half of that to go up and down. 2b squared is 36, divided by a is 8. Now the reason we're not worrying about the plus or minus is because we're not doing a directed distance. We're doing just a normal distance, and normal distances are all positive. So that's why we left the plus or minus off the 8. So the length of your lattice rectum is 9. I'm going to write that down below it so I have more room. Okay. Which means the amount that it goes up and the amount that it goes down is only half the distance of the entire thing, coming from the center. So our up and down is going to be 4.5. So 9 total length, 4.5 each way. 4.5 up, 4.5 down. So on your graph, do the best you can to make your graphs perfectly square, perfectly straight. Just having those diagonals off a little bit can really mess with us. So I'm going to start with the vertex. Center is at the origin, so that's simple enough. Starting with your vertex, that's plus or minus a, and it's along the major axis. Plus or minus 8 along the major axis. So 8 positive, 8 negative. B is your minor axis, so that's going to be plus or minus 6 along the minor axis. Okay. C is your focus. C is again on the major axis. So from the center, it's going to go plus or minus 10. So everything's labeled, your vertex, your B, and your focus. Okay. Next thing we did was our lattice rectum. We found the length of the lattice rectum. So that was 4.5 up, 4.5 down. It always goes through the focus, just like in ellipses. So from here, you're going to go 3, 4.5. It's going to be about right there. 2, 3, 4.5. 2 foci, you've got 2 lattice rectums. So make sure over here you get it going 4.5, So we have the ends of our lattice rectum, we have our vertexes, we have our foci, we have our minor axis. The only thing left is to do the asymptotes. So your asymptotes are from your B's and your vertexes creating a rectangle. Again, try to make your rectangle as perfect as possible. And you're going to go from your center and draw a line all the way through both corners. Should be a straight line. We want the diagonals of the rectangles. Okay. Again, major axis is the X. It's got to go through the vertex. So the last thing to do is to draw the line. Start from your vertex. Draw the line through the ends of the lattice rectum. And then it will follow similar to the asymptotes. Does not get right up on them. Sometimes it does, sometimes it doesn't. Make sure it goes through that. Make sure you have a nice smooth curve. The other side goes through the vertex, through the ends of the lattice rectum, making sure you have a nice smooth curve. So the graph itself is in red. Everything in purple is the essential pieces you need to make sure that graph is as close as you can get it. Okay. We didn't have all the pieces in purple, then I could go and say, oh, you're off by some, but you didn't have all the pieces to know that. So make sure you have everything there. You want your vertex, which is A. You want your minor axis, which is B. Your foci, which is C. And you need the ends of the lattice rectum as well as the asymptotes that are through the diagonals. So make sure you have all of that. Okay. All right, the next example is at the very bottom of that page. 12y, draw the graph of 12y squared minus 4x squared plus 72y plus 16x plus 44 equals 0. It's an extremely long equation, so you'll probably have to complete the square. So keep that in mind. They're very, very long. So the first thing in completing the square we have to do is get our x's and y's grouped together and then get our number to the other side. Since y comes first here, I'm going to leave y first. That probably means that y is my major axis. But we'll have to see how the negatives play out to see what happens there. So we're going to group our y's together. 12y squared plus 72y. Group your x's together, minus 4x squared plus 16x, and move your 44 to the other side. You do always want the square term in front of the not square term. You can't put the 16x in front, so keep it in the right order. Okay. Next thing we have to do is, in order to complete the square, the coefficient for every x squared term, or y squared term, must be 1. If they're the same, you can divide by that number and get rid of it completely. Here you got a 12 and a negative 4. Since they're different, we're just going to factor them out. So if you factor a 12 out, 12y squared divided by 12 is y squared. 72y divided by 12 is 6y. We're going to factor out a negative 4. Keep in mind, if ever your factor out term is negative, you've got to take that negative away. So negative 4x squared divided by negative 4. And positive 16x divided by negative 4. Keep that negative. X. Okay. Now to finish completing the square, we take this, our middle term, divide it by 2 and square it. That gives us 3 squared, which is 9. It's 9 minus, right? If we add 9 to here, we've got to add 9 to the other side, right? However, we're not adding just 9. Since 9's inside the parentheses, you're doing 9 times 12, because 12 will get distributed. So you've got to add 108 to both sides. You've got your 9 here, your 12, that makes it 108. When you do your other side, plus 108. Okay. Same on your next one, you have your minus 4, x squared minus 4x. You take the negative 4, divide it by 2, and square it. Gives you negative 2 squared, which is a positive 4. You add 4 to one side, you've got it added to the other. However, we've got negative 4 times the 4. So that's a negative 16 that we're adding to the other side. Finish completing your square. 48. And then divide everything to make it equal to 1. Divided by 48, you can do 48 divided by 12, that should give you 4. Since the larger number is on bottom, your 4 is going to stay on bottom. Minus should be in the middle to keep it a hyperbola. 48 divided by 4. Equals 1. Okay. You'll see that for a second. I'm going to erase this half of it so that I can rewrite it over and keep the board at my maximum capacity so that I can use the most of the board. Since y'all have video, y'all can always rewind it to see this part if you need to see it again. Or pause. X minus 2. Okay. So now we need to get into the graphing process of it. We need to find A, we need to find B, we need to find C. We need the length of the lattice rectums, make our rectangle, draw our asymptotes, and then finally draw our graph. So we can figure out A. We know A squared is 4, so A equals plus or minus 2. We can figure out B. B squared equals 12, so B would equal plus or minus the square root of 12. They're not always going to come out nice and pretty. C, we've got to use our formula. C equals the square root of A squared plus B squared. So C equals 4 plus 12, which is the square root of 16, which is plus or minus 4. Okay. You do your lattice rectum, get the length of the lattice rectum. Remember that is 2b squared over a. So 2 times 12 over 2 gives us 12. Now 12 is the entire distance, so that's the total. So 6 would be each way. 6 one way, 6 the other way. All right, and the only thing we're missing is the center. Don't fall into this trap of, okay, we can find A, we can find B easily, we can figure C out into the latus rectum, we've got a formula for that, and graph everything from the center. Because our center is not at the origin. Our center is from our equation. And be extremely careful, it is not 3, -2, it is not -3, +2. Remember, the numbers inside, the signs have to be changed, but keep the x value first, and x is always with x. So x has a -2 here, opposite goes in the center, so that'd be +2. Y has a 3, opposite is -3. Okay. So on your graph, for your points, when the center was at the origin, we didn't have any problems. We could just take A, go up 2, down 2, or left 2, or right 2, whichever way we're supposed to go. Take B, go one way, go the other way. Take C, one way, go the other way. Into the latus rectum, went through your foci, and everything was nice and simple. Here we have our center's been moved. So your center is at 2, -3. So what we're going to do, A is always on your major axis. Here our major axis is Y. Because Y comes first. So what you're going to do with your A is you're going to take your center and you're going to adjust the major axis value, which is the Y value. So 2 is an X, we leave it alone. -3, we're going to add or subtract 2 from it. So -3 plus or minus 2. So -2, -3 plus or minus 2. All right. So we know it's going to be at 2 on the x-axis. Then you're going to go down to -3, you're going to go up 2, you're going to go down 2. From the center, always from the center. So -3 plus 2 is a -1. A is your vertex, that is your vertex. Then you're going to do -3 minus 2, that's a -5. Okay. So there's your 2 vertexes. B is your minor axis. So you're going to change the minor axis value of the center. So B, you're going to do 2 plus or minus √12, comma, -3. The major axis value gets left alone. Only the minor axis changes for B. So for this one, that's not something we can figure out nice and easily in our head. So you take your calculator, you do 2 plus the square root of 12, and I got 5.46, so around 5.5. And then that's going to be at the -3 Y value. So plus value was 5.5, so we're going to go 4, 5, 6, a little bit on, 6, 5.5, C, should be somewhere around there. Right? Then you're going to go to the other opposite, so 2 minus the square root of 12. I'm -1.46, so around -1.5. Right? So 1, 2, 1.5 will be around right there. So this is your B and your B. Keep things labeled so that when you go to draw your parabola, you know which one's your vertex, you know which one's your minor axis. If you accidentally draw it the wrong way, you're going to get it completely wrong. So make sure you're drawing it the correct way. Next is your C, that's your focus. C is back to your major axis. So A is major, B is minor, C is major. So for your C, you're going to once again change only the major axis. So that's -3 plus or minus 4. So you're going to go 2, and then -3 plus 4 is +1. -3 minus 4 is a -7. So that's your focus, one at the top, one at the bottom. Since our major axis is the y, it should go up and it should go down. Okay. So now what we have left is your lattice rectum. We haven't done that yet. We've worked our way down. We've done A, we've done B, we've done C. Next is your lattice rectum. We're going 6 each way from the focus. So here, if we went up and down, we'd run into our vertex in our center. Because the major axis is the y, we're actually going to go left and right. So you're going to go 6 points left and 6 points right. So go here. 4, 5, 6 points that way. Okay. Same at the bottom. You're going to go 6 points one way and 6 points the other way. That tells you how wide to make your curve. However, we still need those asymptotes so that after it hits those points, it still stays on key. Your asymptotes are made from the diagonals of the rectangle from the vertex and the B. So you're going to take your vertex and make a rectangle with your B's. Draw your diagonals in. They should go outside your focus, outside your lattice rectum. Outside your lattice rectum. Remember what your major axis is to make sure things are going well. I have to recount that one. That one's wrong. This is how you're finding out when things are wrong and when they're right. This one should have been lower. Same as this one, it should have been lower. At 6. Okay. So here, your ends of your lattice rectum are extremely close to your asymptotes. That's okay. If you don't draw your graph carefully, they'll be on the wrong side of your asymptote. So make sure you know what it should look like. Goes through your vertex and the ends of the lattice rectum following your asymptotes. Through the vertex, through the ends of the lattice rectum. Does not have to be perfect. Just make sure you have all the information there so that I can look at it and say, yes, you have everything, you're good to go. Doesn't matter if your lines are perfectly straight or not. Make sure the diagonals go on the inside of the focus. Okay. The next one's a word problem on your test. I'm going to put the numbers. I'm going to tell you to graph them. I'm going to tell you to find the lattice rectums, find A, find B, find C. Graph it. I'll tell you to find the equations. Your homework will go through that. You'll have to use your 2 formulas from page 134 to do the equations to the lattice rectum. It only adds 2 more steps. If we were to, the equations of the diagonals. If we were to find the equations of the diagonals there, so you at least get to see one done, we're going to take our formula. Major axis here is y, so we're using the bottom 2 formulas from 134. That is y equals a over bx, and y equals a negative a over bx. We know a, we know b. So you get y equals 4 over the square root of 12x. 2 over the square root of 12x, I'm sorry. Make sure it's a, not a squared. And y equals a negative 2 over the square root of 12x. For your diagonals. That's all you're going to have to do. Okay? So on your homework, make sure you get that finished. Make sure you email me with any problems like I put on the last video. My email is JELaughlin, JELAUGHLIN @dcccd.edu. Make sure you email me. I have my phone, which gets all my